All right, let's talk a little bit about implicit differentiation. Now, up till now, all the equations we've been able to solve for y. But when that's not possible, it becomes a little more tricky. The equation for this, a circle with radius 5, is x squared plus y squared equals 5 squared. Now, we're going to take the derivative of this implicitly. We're going to take the derivative. We're going to take the derivative of x squared, which is 2x. We're going to take the derivative of y squared. Since the variable is not y, we're going to have to use the chain rule. We're going to go, okay, it's going to be, the picture is something squared, so it's 2 times the something to the 1, times the derivative of the inside. So it's going to be times the derivative of d of y, excuse me, with respect to x, equals, and the derivative of 5 squared is 25, and the derivative of a constant is 0. Now, if we solve for the derivative, we can subtract 2x from both sides, and we get 2y dy dx is minus 2x. Divide by 2y on both sides, and we get dy dx, the derivative, is negative 2x over 2y, or simplifying, the 2's can cancel, negative x over y. Now, this is not strictly a function of x. It's x and whatever y is. Now, we could solve for y in here and replace that. Subtract x squared from both sides. We get 25 minus x squared is y squared, and then take the square root. But when we take the square root, it's plus or minus, and so sometimes we want to use plus the square root of this, and sometimes we want to use the minus. So I'm going to stick with this for it. So I'm going to go up to the graph now, but I'm going to mark down that the slope dy dx of any place on the circle is negative x over y. So here's a point on the circle, 0, 5. And it looks like the slope there of the tangent line is 0. If we put 0 in for the x and 5 in for the y, we get negative 0 over 5, or 0. So this does tell us the correct slope there. If we go to here, the slope is undefined. It's a vertical line. And if this point is 5, 0. So if we put 5 in for the x and 0 for the y, we get division by 0, which is undefined. But let's look at some other places. Like, let's look over here at minus 4, 3. Minus 4, 3. So if I put in minus 4 for the x, I get 4. And I put 3 in for the y, I get 4 thirds. So if I start here and go up 4 and over 3, does that look like a tangent line? And it certainly does. So this will predict the slope for points on the curve as long as you figure out both the x-coordinate, minus 4, and the y-coordinate, which is minus 3. This will give us the slope at that point or at any other point. So the real difference is, instead of just knowing the x and plugging it in to find the slope at that x, we find out the slope at points by doing this implicit differentiation. The big difference is we take the derivative of x, well, that's the variable is x, so we don't have to do anything extra. But when the variable is y, we have to say times the derivative of the inside, which is dy dx. Let's take a look at another one. That one, these are kind of straight from the book. Here's one that had this equation, and it's in the book. So I plotted it on Desmos, and I clicked on some of the points where we might want to find tangent lines. So let's find the derivative implicitly. The derivative of x to the third is 3x squared. Since it's x, we don't have to do chain rule, or we could say dx dx, but that's 1. Plus the derivative of y squared is 2y. That is y, so we have to go dy dx. Then we have a product here. So I'm going to think of this as 2x and a y, and it's subtracted, so I'm going to go. The product rule is the derivative first. Derivative of 2x is 2 times y, plus the derivative of the second part is dy dx, 1 dy dx, times the first, and that would be the derivative of this product. The derivative of the first times the second, plus the derivative of the second times the first, equals, and the derivative of 2 is 0. Now I'm going to solve for dy dx, which would tell me the slope. So I have 3x squared plus 2y times dy dx minus 2y minus 2x times dy dx, distributing that minus, equals 0. So the parts that don't have dy dx times them, these two parts, I'm going to leave here. The parts that don't have it, I'm going to take them to the other side by subtracting 3x squared and adding 2y to both sides. So I'm going to get 2y, and then I'm going to factor the dy dx out of these two. So I'm going to have 2y minus 2x. Those two are both times dy dx, and I'm going to take the 3x squared to the other side, minus 3x squared, and I'm going to take the minus 2y to the other side by going plus 2y, and then I'm going to divide by that, and here's what will predict the slope of a tangent line. So now, if I want to know, and none of these points are very pretty, that happens to be the square root of 2. I recognize that decimal. So let's figure out the slope here at 0 square root of 2. Now it looks like the slope is about 1-ish there, maybe a little less than 1. Let's figure out what that is. So using my equation for the slope, minus 3x squared plus 2y over 2y minus 2x, figuring it out here, I'm going to put in 0 for the x's, so that'll be gone. I'll have 2 times the square root of 2 over 2 times the square root of 2 minus 0. Oh, that's 1. So the slope right here is 1 over 1. And I could put this in for x and this in for y, so I'd get negative 3 times that number squared over minus 2 times that number. and 0's in for the y, and that should give me the slope there. If I wanted to know the slope here, which is 0 minus the square root of 2, looks like I should get 1 again. 0 in for the x is gone. I'm just going to be putting minus the square root of 2 in there, and both of these would turn to minus, and so they would cancel, and I'd get 1 again for the slope. If I put this in for the x and that in for the y in both the numerator and the denominator, the numerator should come out to be 0 because that looks like where the slope is 0. And so taking the derivative implicitly, just taking the derivative, and if there's a y, multiply by the derivative of the y, dy dx, in it, and then solve for dy dx by this process, you can find a way to find the slope any place on a graph that's not a function. It's not a function because it doesn't pass the vertical line test, but you can still find the slope at different places. Here's another fun one that's in the book. And this goes through some nice places like 2, 0, 2, 2, 0, 1. Oh, this would have been 0, 2. I said that wrong. This goes through 2, 1, and 2, 0, and 1, 0, and 0, 0, and 0, negative 1, and looks like it goes through a nice place there, 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 there. I could find the slope at all those different tangent lines. Now, this is what the book gave for the equation for this. I could multiply this out, and I get something that looks like this. Or I could use the product rule or the enhanced product rule. Derivative of this times these two plus the derivative of this times these two plus the derivative of this times these two. Or, and same over here, or I could just take the derivative of this and the derivative of this. I'm going to do this. Either the book does this one. The derivative of this is going to be 4y to the third dy dx because that's a y. But all of these are y, so they're all going to be times dy dx. The derivative of this is going to be negative 6y to the second. The derivative of this is going to be minus 2y. The derivative of that's going to be plus 2 times, each one of these would have been times dy dx because the variable was y and not x. The derivative of each one of these is just going to be, without a dx, it's going to be times dx dx, or 1. So it's just going to be 3x squared plus minus 6x plus 2. So to solve for dy dx, I just divide by this. And that's how I can find the slope. So I'm going to write that over on here. The slope at any point can be found by doing 3x squared minus 6x plus 2 over 4y to the third minus 6y squared minus 2y plus 2. Now, before I go on doing this, how do I know these are the points? They look like it. Well, what makes this 0 is y could be 0, and it has 4 places. Y could be plus 1, has 4 places, or it could be plus 2, has 4 places. Those are what make that side 0, and what makes this side 0 is 0 for x. So there's 0 for x, 3 places. At 1 for x, 1 would make zeros, 1, 1, 1, 1 there, and 2 would make x zeros. And these, I should have said this way. But anyway, so they're all related to the factored form, and that's how they made it go through these nice points. They used the factored form. I multiplied them together. But anyway, what's the slope look like it is right here? Let's say. That looks like about -1. Let's see what it really is. Put 2 in for the x's. So we get 2 squared 4 times 3, 12. 2 for the x, -12, plus 2, over, for the y's, I have to put 1, so that's going to be 4, -6, -2, plus 2. Those cancel out, those cancel out. I get 2 over 4 minus 6 is -2, so I get 2 over -2, which is -1. Slope here at 1, 0. That looks like it's about -0.5. So I'm going to check the slope at 1, 0. Put 1 in for the x's, and I'm going to get, for here, I'm going to get 3 minus 6 plus 2 over zeros in here will be just a 2. 3 minus 6 is -3 plus 2 is -1 over 2, slope of -1/2. I could put in 0, 1, I could put in 2, 2, I could put in 0, -1, and I would find the correct slope for each of these places. This will predict the slope of this graph, as long as I know the correct point that I want to find the slope at, the x and the y, and plug it into that equation. That's the power of implicit differentiation.